substituted the Taylor rule in, and you can then write the model in this form here, where we have a vector of two endogenous variables, y t and pi t, that depends on the same vector in the future. Right? We have our forward-looking households, consumption savings. We think about what we want to consume in the future to decide how much to save, how much to consume today, and our forward-looking price setters. When we set our price today, we take into account that we might not be able to change it in the future, so we want to make sure our price today will also be an okay price based on our expectations of the future of the economy. And some exogenous processes. One, this monetary policy shock. Remember, a mistake, a mismeasurement, or political pressure that causes the interest rate to jump and change unexpectedly. And this natural real rate that depends on the growth rate of technology. It's also why I'm so thirsty. Okay, we saw that if we look at some other process, xt equals a, et, xt plus 1 plus b, zt. Right, that we can write this then as equals the limit to infinity we solve this forward, right? And it depends on being able to write this dependent on this number, a, the scalar being less than 1. Now, how would we go about doing this now if we have two variables? We have a vector of variables, and instead of one number, a, we have a matrix. So, we can think about a scalar a to the power of j. All we need to do is think about a matrix to the power of j. So I'm kind of visual in this respect. If I think about a matrix, I take a matrix squared. I take the first row of the matrix, multiply it with the first column of the matrix. That gives the first one. Then the first row, the second column, to the second entry. Then the second row, the first column, gives me entry down here, and the second row with the second column gives me the last entry there. That's kind of complicated just for the square. How about we do that j times? I'm not sure how to write it out in closed form. This is going to get very complicated. We already, with the squared, we have products and sums. Right? Just writing out the square of a matrix in terms of the individual entries is going to be pretty complicated. Right, so how can we think about, just make sure I write this in the right order. So now we have xt, where this is the vector of our y, output gap, and inflation, equals a. I'm going to drop this. This is in the book. I don't like this t. It's always confusing anyway. But write a capital letter t, xt plus 1, plus b, zt. Good morning. Right, with this zt, we can simply write as the difference between RT and mu t. So it looks like a V, but it's a Greek mu, like the Gesundheit. We ran out of like Latin letters, right? So we use Greek letters too. There aren't a whole lot of them, I think. So because I've been learning Japanese, and Japanese has 3 alphabets, one of which is the Chinese alphabet. I always suggest to colleagues, let's just start using the Chinese alphabet. We'll never run out of letters then, right? Not yet, maybe in 20 years. Yeah? Okay, so we somehow need to talk about this A being less than 1. Yeah? And the reason this less than 1 is important is that it converged in the limit to 0. Yeah? And so this geometric sum also converged. So we need to think about this for matrices. Let's make the problem simpler by first making it more complicated. So let's find, I mean, let's write A in this form, where the elements, or no, capital lambda here. So these are all 2 by 2 matrices, signs inverse, and lambda is a diagonal matrix, and the elements of lambda satisfy I and so V, capital V matrix is then V2. This is then a 2 by 1 vector. So we have these so-called eigenvalues and eigen vectors. They might also be called the characteristic values and characteristic vectors, depending on how you learned it. This is neat because this is German. Yeah? German was the language of mathematics up until 1933, 1945. Then Second World War, and people stopped using German in mathematics. But a lot of the key terms from the beginning there were written in German. So let's see, this kind of cute story. Let me show you. this is my grandfather's PhD thesis. He was the first in our family to get like he got a PhD, but he was his parents were farmers, and actually was raised by, his parents got divorced, and blah, 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 lots of, but this was his PhD thesis from 1956. He did aeronautical engineering.
Wow.
They do that all by hand, right? Equations, stuff like, okay, fine. But the reason why I'm showing you this is when you look at his, no, this is just a paper. This isn't the thesis itself. So this is the actual dissertation he submitted in 1954, and his references. So look at the way you have to write equations back then. We didn't have LaTeX. Right, so his PhD thesis, he had to handwrite it all in, the typewriter, and you space there with the
Anh kia giống như là
That's
hỏi
how
lại
you
rồi
do it.
đó, chứ không
What?
phải ai mới đúng, hiểu không?
When we look at, there's not a lot of
Cái này là
literature, right? There was less literature there, but it's about, airplanes flying at Mach 1 of this. And then when you go to the map literature, he's citing Georg Hammer Integralgleichungen, Berlin 1937. Right? So still in the 1950s in America, the mathematics literature was still all from even after the war, right? Because that's where all the mathematicians were, and that's where the results were published. The big advances in math at the beginning of the 20th century were in Germany. So it was useful at this point in time to speak German for the math literature, for science. It was a language of science. That's no longer the case now. At the German university, right? English is now the international language of science, which is, even though it's a partnership with Germany, we communicate in the modern language of science, which is English, right? But if you go back far enough, not too far, you'll see that used to be different. Okay, so that's a long story, or a short story, as to why we've got the German here, the eigenvalues and the eigenvectors. Eigen means own, yeah? Own, so my own. So it's eigen, so it's my own, it's what defines me or belongs to me. Yeah? So these are the values that belong and define the vector, right? And we have these principal values, these characteristic values, these own values, and then, right, we move them into a vector space, these eigenvectors. Okay, so we can calculate these, right? So we need to find non-trivial values that satisfy this, or non-trivial vectors. So we need this to be, right, so if this times this is equal to 0, if this is a non-trivial vector, then this has to be equal to 0 in some sense. Right? We have this 2 by 2, right? So we need the determinant. So I solves the determinant of I rho minus A equals 0. Yeah.
That is not z with the index of 2 plus j minus 1, right? Tomorrow, yesterday we did
No, we haven't solved this yet.
before. I just like
This one here? Yeah. Here?
z plus j minus 1.
Limit.
Yeah, that last term. Yeah, the index of the z there.
Yeah.
Now, yeah, z plus j minus 1. Yesterday we did
Có mà.
Shouldn't be. I forgot to put the notes from the forum yesterday.
À, if we assume that JT is IID, so will not. But here we did not assume that is a ID, so we keep the
That's right, so there's a special case if it's
Yeah,
with an
yeah,
IID,
yeah,
but
yeah.
here I wrote the general case.
Yeah.
Unless I wrote it incorrectly. Okay.
But it's just ý là tại vì assumption là cái đó ID thì cái expectation nó bằng không.
So
ID.
that's right. This first term is that if A is less than 1 in absolute value, this is 0, so it's the same expression as there. Yeah? Well, good to ask, because I make mistakes all the time. All right. So we can solve for the eigenvalues. Let's we can do and if we have a matrix for A equals A11, A12, A21, A22, right? We can write this then as the determinant of rho minus A11 minus A12 minus A21, rho minus A2. And the determinant is the diagonal minus the cross diagonal, or the anti-diagonal. So this gives us then rho minus A11, rho minus A22, minus A12, A21. Right? And we're going to require this to be equal to 0. So we need that 0 equals rho squared minus A11 plus A22 times rho plus A11 A22 minus A12 A21. That's one sort of complicated calculation here, but the key thing we should see here is a quadratic equation. The quadratic equation has two solutions, rho 1 and rho 2. That's how this all fits together. Now, why is this useful? This is complicated, right? But why does this actually help us? Something cool happens, right? A squared, right, is A times A, right? This would be this rows times columns, that's kind of complicated, but now we can write this as V times lambda, V minus 1, V lambda, v minus 1. And that part, Gesundheit, drops out. No? So we're left with v lambda squared, v minus 1. Right, we can do it. Another time, a cubed, a times a is v lambda v minus 1, v lambda v minus 1, v lambda v minus 1. And we have now two of these pairs that cancel out. And this is simply then v lambda cubed v minus 1. Well, wait a second. How is this any simpler? Now instead of having to figure out maybe what a to the power of j is, right, we have v and lambda to the power of j. But lambda is also a matrix. Right? How has this helped us?
Power the element.
I'm sorry?
I mean the power the element inside.
Yeah. Lambda isn't just any matrix, it's a diagonal matrix. So lambda j equals these elements to the power of j. That we can do, right? So now, well, this kind of makes sense. We have a vector, we have two variables, and so we kind of need to find two different a's. Yeah? And both of these a's need to be less than 1. In absolute value. All right. So now, if rho I is less than 1, for I equals 1 and 2, so both of these are less than 1 in absolute value, right? Then the limit as j goes to infinity of lambda j is equal to the zero matrix.
Yeah.
And thus, a to the power of j, limit, is also, right? Just goes to the zero matrix. So using the same logic that we have before, we can now write that xt is equal to let's do it with be a little more careful. Right? With matrices, the order of multiplication matters. Right? A times d is not the same as d times a. Right? That's the one commutative. Right? That property gets lost when we go to higher dimensions. So let's just review real quickly. I'm just solving forward. Just recognize the pattern. So e t x t plus 1 is equal to a e t x t plus 2 plus d e t zt plus 1. Plug this in here. We get then that xt is equal to a squared et x xt plus 2 plus d zt plus a times d et zt plus 1. Alright, so I'm going to make the, well, you can do another step until you see the pattern. Xt is going to be equal to the limit as j goes to infinity, a to the power of j, et xt plus j, plus the sum of j equals 0 to infinity of a to the power of j times d et dt plus 1. Alright, so we can't pull this d out in front because it's matrices and we don't have commutability. That's why it looks just a tiny bit different from that, but it's the same thing. And so now we understand the properties of a to the power of j. So now we can write if both, what do I call this row? Oh, that was sort of silly. I should call it lowercase lambda, that would make more sense. Oh well. No, I'll just keep it then. Okay, if both rho I and lambda are less than 1, and absolute value, right, then xt equals g plus j. Right, and if zt is iid, then we have xt is equal to then higher expectations. Right, so we just have b zt. Since you've seen the magic of time series econometrics, right? With you do time series econometrics with Uwe Hassler or Mika Binder, right? So let's assume that ZT is a VAR1 process. VAR, yeah? Let's call this an so then we can calculate the expectations, right, of then zt plus j is simply equal to rho the power, or p to the power of j times zg. Right, and xt is then equal right, so we see some sense, in some sense, based on the predictability of z, it's always going to be then come back to being dependent on something we can observe today. Well, we have to take into account this correlation pattern. But we see that then this forward solution is telling us that xt is a function of zt. Xt is a function of zt. And here we can work out directly with matrix algebra, with linear algebra, what that solution is. there's also an alternative, namely, well, if we know the functional form of the solution, so xt is some function of zt, right? It's a linear function of zt. Right, then we're going to solve the model. Right, we could do this approach and factor. We're going to have to do lots of linear algebra and stuff, or we can take a different approach now, know the form of the solution. Let's just go shock by shock. Right? We know that the endogenous variables, pi t and y tilde t, those are the elements of this xt vectors, are just some functions, linear functions of our shock, which are our shocks. Right? So let's look at the response to a monetary policy shock, and our endogenous variables are going to respond to this policy shock in a linear contemporaneous form. And now all we have to do is determine these coefficients. Right, so this solution method is called the method of undetermined coefficients. We guess or know the form of the solution, and then we resolve the conditions under which this guess is true, right? Or we determine the values of these coefficients. Okay. Now there's something economically very special about these eigenvalues being less than 1 in this forward solution. Right, here for this model that we have with our specific A matrix, with our forward-looking Keynesian curve, Phillips curve, our forward-looking dynamic S equation, and our Taylor rule. The condition on the parameters, right, that show up in our A matrix. Right, so it's omega times these four things. We can show that that has two eigenvalues that are less than 1 in absolute value, if and only if this inequality, in 54 holds. And to see what this means for a second, set phi y, so that's the response of the interest rate, to the output gap equal to 0. Well, that term then disappears. So for 54 to hold, it must be the case that phi pi is greater than 1. Phi pi greater than 1 means that monetary policy must respond to inflation, but with sufficient vigor. It has to respond strongly. Not just a little response, but it has to be aggressive in its response to inflation. The response has to be more than 1 for 1. So for any increase in inflation, the nominal interest rate must increase by more than that amount. Why is that intuitive? We thought about, when we talked yesterday, if this condition does not hold, then we have these bubble terms, this extra shock that is just an expectations or belief shock, right? And we have nothing to pin it down. So what this strong enough response does is it eliminates the possibility of such a belief shock. And to think through how this might work, imagine this case of where we all think inflation is going to be higher. Right? So if we think inflation is going to be higher, and we all raise our prices, then inflation is higher. Right? And we've now have a self-confirming, a self-fulfilling belief shock. Okay, so let's say we believe inflation is going to be higher. But now, we're going to take into account monetary policy responding more than 1-for-1 to inflation. So look at our IS equation. Why don't we put it back to the form that might be in bigger font, familiar with, from our consumption savings equation here. So now we have inflation goes up, but the interest rate goes up by more. If the interest rate goes up by more than in belief in inflation, then the real interest rate
Negative.
increases in response to this shock. Okay? So now we want to think about our households, demand for goods. What happens if the real interest rate goes up? If you're a saver, now's a good time to save more. If you're a borrower, it's expensive to borrow, so you're going to borrow less. In both cases, your demand for goods today, YT in total, is going to go down. So now think about us as firms. We thought the prices were going to go up. In response to this belief, demand for our goods goes down. This would tend to do what to our prices? Push them up? No. Push them down. When fewer people demand our goods in the market, we're forced to cut our prices. And so what we see is that our belief shock is no longer internally consistent or self-fulfilling. Because monetary policy responded strong enough, our belief that wasn't supported by fundamentals, we woke up in the morning and thought prices are going to go up, monetary policy responds strongly enough to ensure that prices come back down, stabilizing and eliminating this belief shock. If monetary policy does not respond more than 1-for-1, then we would have interest rate goes up, or inflation goes up, and the interest rate goes up, but not by as much, so the real interest rate goes down. If the real interest rate goes down, if I'm a saver, bad time to save, I'm going to save less, so consume more. If I'm a borrower, cheap to borrow, I'm going to borrow more today to consume more. In both cases, demand for our goods goes up. And so now we believed, for some random reason, that or non-fundamental reason, that inflation was going to go up, and this caused demand for our goods to go up, which of course drives up our prices, confirming this self-fulfilling belief shock. It's now internally consistent. Now, so monetary policy, by responding sufficiently strongly enough with the nominal interest rate to inflation, breaks this consistency, breaks the ability of such a non-fundamental or bubble belief shock to be supported by the economy. And hence, these shocks never occur in the first place. So this gives us then a unique equilibrium. And we think about why this is important for monetary policy. Right, there might be some reasons why we want to respond a little bit more strongly to inflation, or a little bit less strongly with the output gap as well, right, depending on, I don't know, maybe, right, we've had problems with inflation in the past, so we want to show that we're really going to fight inflation, so we want to set this response to inflation really, really high, right? Or maybe our current premier or prime minister has a strong interest in output growing along, staying with its growth path. And you've got growth path projections maybe 10%, and it's important to keep the economy growing at this speed. So maybe we respond very strongly to the output gap. These are all true and very important. If we don't, however, satisfy this condition, then we can't say anything about what the equilibrium is going to be. The output gap could be this fundamental level, right, staying on the growth path, but it could be any other level at any point in time, depending on what people believe. So this is a problem for policy, right? Then, we could think about, again, picking out a specific combination that we want inflation in the output gap to satisfy by choosing these parameters. But then the question is, can we ensure that this combination that we pick actually comes about? If we satisfy this inequality, the answer is yes. So then if we satisfy this inequality, and by choosing different values of phi y and phi pi, this will lead to different interest rates, which will lead them to different equilibrium values of inflation in the output gap. If we don't satisfy this inequality, then different combinations of phi pi and phi y would be consistent, maybe with different levels of output, the output gap and inflation, in the absence of belief shocks, but we also have an entire continuum, an infinity of other possible equilibria with different amounts of inflation in the output gap that depend only on what people believe. So uniqueness allows us to ensure that we have a single equilibrium, and then we can pick which equilibrium we want as policy by choosing our parameters. If we don't have uniqueness if we don't satisfy this inequality, then we can't make any prediction about where the economy is going to go. Right? So, it'd be kind of important. So in other words, this is a scary thing, if you've ever been like on a bike or motorbike or a car when the steering wheel breaks. Right? You're used to turning this thing and the vehicle turns. Right? But if you're like, it's never happened in a car, thank goodness. I've never been on but it's happened in my bicycle, where I turned my steering, my handlebars, and it came loose, right? And so I'm turning my handlebars, but the wheel's not moving. That's a very scary thing because you realize you have no control. You can't steer your bike where you want it to go. That's what happens if this inequality isn't satisfied. Essentially, our policymakers, they have these handlebars, and it has no influence. Right? The bike's going to go wherever. They can't control it. So this is necessary for our policymakers to be able to control and influence the economy. Okay, so now let's look at the responses to specific shocks and some specific assumptions. So we're going to look shock by shock. Let's start off with a monetary policy shock, this new. And let's assume it's an AR1 process. All right, so you can think of now a positive realization of the shock in the process being a contraction in monetary policy shock. Because a shock, positive shock epsilon, means that mu goes up, and ceteris paribus, then I would go up. Interest rate going up would be a contraction in monetary policy shock. Right, but we're not sure, right? It would imply an increase in interest rate for a given inflation in the output gap. Given inflation in the output gap. Well, but likely, they're not going to stay constant. Likely, inflation in the output gap are going to change in response to the shock nu, and so likely our shock I is not simply going to move with nu, there's also this component here. This is what picks out the equilibrium by monetary policy, this is what ensures stability. This is what we call the systematic component of monetary policy. Systematic, in the sense that it's not chosen discretionarily, it's not chosen at random, it's a form of commitment of monetary policy. When inflation goes up, we respond with phi pi. It's like a promise by monetary policy. And it's a promise here, because we've written it mathematically, that the monetary policy will keep. Okay, so we have a contractionary monetary policy shock, a realization epsilon nu, positive, drive up nu, drive up in the interest rate, first holding inflation output gap constant. Now the natural real interest rate depends only on changes in productivity, and we're holding that constant. Right? We're just looking at a shock to monetary policy here. So that means the real interest rate stays constant. Right? We just have the shock to nu t. Right? So we can think now, if we read this system, we'd be defining zt. Right? We're going to hold productivity, hold the real interest rate constant. So zt would just be a scalar equal to nu t. And we're going to use this method of undetermined coefficients. And okay, so we're going to see how this works. So we're going to use the form of the solution. We've already convinced ourselves, hopefully, that the response of our variables has to be linear in the shocks. So we're looking at a shock, a realization of a shock to mu t. So the output gap and inflation are going to respond in a linear fashion to this shock. Right, so we have psi y nu and psi pi nu. Right, so this psi, these psi's are unknown coefficients. Right, we don't know what they are. That's what we're going to try to resolve. Right, so we're guessing, or we know that the solution form has to be linear. Right, so now we're just trying to figure out the slope. This is useful as a way to help us resolve these expectations. So if this is true, and we're assuming it's true, then we can calculate the expectation of the output gap tomorrow straightforwardly. The output gap tomorrow is going to be psi y nu vt plus 1. And the expectation of today of nu t plus 1 is simply rho nu t, because this AR1 assumption. So we can directly write out that the expectation today of the output gap tomorrow is this unknown coefficient times the autocorrelation of monetary policy shock times the realization today. Right? Or in other words, in expectation, we're just looking at one shock, so the response tomorrow is simply the response to the shock today. And it's how yt responds to the shock tomorrow, which in expectation, because the autocorrelation is simply going to be this autocorrelation times its value today. This is useful because we can now plug the form of the solution into our equations. So again, the new Keynesian-Phillips curve, instead of pi t, we have nu pi, or psi pi nu, this unknown coefficient, times vt. Then we have beta times expected inflation, and that's this unknown coefficient, autocorrelation vt, and then kappa times the output gap. And if you notice here, this equation is homogeneous in nu t, in the shock. Right? This equation needs to hold for any value of the shock. Right? Whether the shock is +1, -1, plus 0.1, plus, so that means the coefficients underlying it have to satisfy this equation. If this holds, then this equation will hold as well for any realization of nu t. All right, so now our new Keynesian-Phillips curve gives us a, look at this, a deterministic, it's no longer stochastic, these aren't variables, this is just an algebraic relationship between two coefficients. All right, this has resolved this expectations in the stochastic problem for us. Now we have one equation in two variables. All right, so we need a second equation. Indeed, we have the second equation from our new Keynesian IS curve, the dynamic IS curve with the Taylor rule plugged in. All right, and we can start to collect the YTs on one side. Right? And now we can plug in this form of the solutions, replacing yt with the unknown coefficient times the shock, unknown coefficient autocorrelation of the shock because it's expected value of yt plus 1, and the same with inflation, and we get then here another deterministic equation. Right? We've resolved expectations, we've resolved the stochastics in the model. It's now just a simple linear algebraic equation. Right? We can rearrange this, and we have now another linear equation. Right? And this is fantastic. Right? If we write, if you do this graphically, psi mu and psi y mu. I'll do this then. Right, this gives us a positive equation that goes to the origin. Right, a bit of it around. Phillips curve, we get a relationship like this. And from the IS curve, solve this through slope. Right, which means we have a unique value of each of these coefficients that satisfies both equations. As we'd expect, in general, two equations and two unknowns. Right, they're linear. That's what you can think of in the special cases when they wouldn't be solved with equality. Right? If these equations were collinear, like they're parallel, right? There wouldn't be an intersection, or if they're exactly the same, right? Then there'd be an infinite number of solutions, but that's not the case, right? They're clearly positive slope, negative slope, different intercepts, so they're going to intersect somewhere. All right, we can work out if it's just cranking out algebra like you did, when you were 14, right? 15, 16, 12, a while ago in any case, right? Cranking out the algebra to solve two equations, and we get then that psi y nu has this value, right? Okay, we got a lot of parameters in there, right? And psi pi nu has this value. Right? If our Blanchard-Kahn condition, this was the condition that ensured uniqueness, right? That in this model is satisfied by a more than 1-for-1 increase in the nominal interest rate in response to inflation, also known as the Taylor principle. if that condition holds, which it needs to for there to be a unique equilibrium for our solution form to make sense. Remember yesterday we saw if A is greater than 1 in absolute value, right, then writing our solution in this form doesn't work. We have to add in this expectation shock. Okay, so we need that to hold, and if it does hold, then this collection of parameters in lambda nu is positive. So the output gap and inflation, both of their parameter, these in the unknown coefficients, are negative. Okay, so what does that mean? If we have an exogenous increase, right, to our interest rate shock that's positive, this will lead to a fall in inflation and fall in the output gap. Right, so a surprise increase in the interest rate is going to bring down inflation, right, and it brings down inflation by reducing demand. All right. Also important here, this is the response of the output gap. And in this case, the output level itself responds in the same way. The output gap is the difference between actual output and the natural level. Right, the natural level is the level of output that we would have in the absence of price rigidities. And we saw that this level depends on and only on the realization of productivity. Right? It's driven by real factors. So if we're just changing monetary policy, if we just have a new shock, a shock to the interest rate, we're holding everything else constant, every other exogenous process constant, including then here productivity. So we have in this case, the natural rate of output stays constant. So if the output gap goes down, that means that the actual level of output also goes down. Okay. The real interest rate is also going to rise. This is rise unambiguously in response to the contractionary monetary policy shock. So we have look, this whole term here is the real interest rate. Right, so we can bring it to the other side. Right, because we have to avoid this constant, and so we can write down the response. Real interest rate equal to sigma times dy plus 1 is y tilde minus y tilde t. right, with the form of our solution, we know that this is then psi y nu times rho minus psi y nu times nu t. The autocorrelation has to be less than 1 for this to be a stable process, we assume. So this is negative. This is also negative. So for a positive shock, that has to be positive. Right, so we have this mu, 1 minus rho, square minus rho nu. Right, and here we have this psi y nu. Okay, now how about the nominal interest rate? The reason why this is perhaps not straightforward, we go back to our Taylor rule. We have a positive shock to nu, and we've just determined by its contraction x, this is going to drive down demand, drive down inflation. Pi and y tilde are going to go down. So look at equation 51 for a second. This goes up, but these two go down, moving in opposite directions. Oh, so whether the nominal interest rate in equilibrium actually goes up or down, it's going to depend on which of these two effects are larger. We have the same sort of thought process like we saw with government spending multiplier. We have a direct effect, right? The direct effect of the shock in the nominal interest rate, and then we have general equilibrium effects, so the second round effects. It's not the construction workers and the asphalt factory owners with more income, right? It's a different equilibrium process, but it's this change here. In the first round would lead the interest rate to go up. In response, the interest rate going up, this reduces demand, reduces inflation, which would tend to push the interest rate down. So that's called a general equilibrium effect. Right? And these general equilibrium effects can go in the same direction or in the opposite direction. Most of the time, general equilibrium effects, if they go in the opposite direction, will not be larger than the direct effect. Most of the time. They'll simply reduce this direct effect. And you can think about why this is probably going to be the case by going through this logic again. So we have a shock. It increases I, which would tend to decrease pi and y tilde. So the indirect effect now would tend to reduce I from where it would be from the direct effect. Well, if we reduce I, that means the effect that I had on pi and y tilde through equilibrium, right, the contractionary nature of this monetary policy shock has now been reduced. So the reduction in pi and y tilde would tend to be a little bit less than that first round effect. So you can see that, like, as we start to go through this logic and figure out the equilibrium, there's going to be smaller and smaller adjustments. It's simply adjustments. So the indirect effects of general equilibrium effects is going to reduce perhaps the magnitude the scale of the shock nu on the nominal interest rate I, but it's generally not going to reverse it. Right, and when we write out the coefficients, when we solve for this equilibrium value, we're going to find that, there is some case, Gesundheit, some cases where we can make an overriding of this, this effect. So the equilibrium effect can be larger, but only for very, very persistent monetary policy shocks. Okay? So if rho mu is very large, then we will have potentially a negative response in the nominal interest rate today to this surprise shock. And that's simply because then, with a very high autocorrelation, this means that the fall in inflation is very large, because inflation depends on our expectation of future inflation. And if we have a large autocorrelation, this is telling us that, well, we have a contractionary monetary policy shock today, and it's going to be contractionary tomorrow and the day after, right? And very, very strongly. So our price setters who can't adjust their prices are going to respond by lowering their prices, not only in response to the contractionary policy shock today, but they're going to front load all of these future expected contractionary monetary shocks. Right, so we're going to have a very large drop in inflation today. Output, right, is still going to output is going to fall because we have this real interest rate effect that's unambiguous, as we saw. We're going to add into this a money demand equation. So if you look back last week at our LM equation, you'll see that it was downward sloping in the nominal interest rate. And that's exactly what we have here. So the slope eta, right, is the semi-elasticity of money demand with respect to nominal interest rate, and we have this effect, we can shift out the money demand curve. When y goes up, this transactions effect. Right, we can think about adding a demand for money into the model. Right, so have this there are a couple different ways to, why do people hold money? How can we add this into our household optimization problem? We could have, there are a number of different ways that are going to give us the same answer. So let me just think about this intuitively with you. Our households care about consumption, right, and labor. We want to consume a lot and not work a lot. Maybe there's a third motive, and that's we value having purchasing power. Right, so, you know, it's nice, I feel happy when I can consume something, when I can buy something, but I also feel happy knowing that I could go out and buy something. So I don't have to, you know, I don't know, buy a fancy dinner, but it makes me feel good knowing that I could if I wanted to. You know? If we added that motivation that the household prefer to, or has a preference for a real balances, we can then derive equation 63. Or we can have a requirement that we have a cash in advance constraint. Right? When I think about my purchases today on campus, I have to make sure at the beginning of the day I have enough cash. I don't have time to go to that ATM. So I want to get some drink, I want to get some lunch, I need to get some dinner. I need to make sure I have enough cash because I don't have access to your QR payment system. Right? So that would be cash in advance. And determining then how much money I'm going to demand from this motive is going to be equation 63. Or we could have a transactions effect. This is what we see. All right, so let's assume that I have access to the ATM. I I could go to the ATM in the morning before I have breakfast, then go back to the ATM and get some cash and go to the little convenience store to get some water and a Coke. Then I could go back to the ATM, get some money for lunch, and then go back again, right? I could go to the ATM 5 times in a day. Usually we have to pay a fee when we go to the ATM, or I have to walk there, it takes time. In either case, it's costly to go and get cash. So I'm better off getting a larger amount of cash at one time. How large, how many days in advance of cash should I get? Well, first I need to know the transactions that I'm going to have to cover. 3 days transactions or 2 days transactions. And then, what else am I giving up? If I take out enough money for the whole month and hold on to it, that's a significant amount of cash that I could have been earning interest on. So I'm going to have an opportunity cost. That would also give me equation 63. All right, so there are a number of ways we can get there. It's not so important for us. It's important enough for me to talk a couple minutes to you so that you realize that this can be motivated or this can be incorporated into an optimization problem. Right? And you can think about, well, maybe some of these explanations make more sense in my country and my economy than others. Right? Or we could ask ourselves, what's going to happen if we have, we assume that money demand is based on these transaction effects, but we have cashless transactions available. This might change our money demand equation. That might be interesting for monetary policy. So things that you would think about for projects, seminars, or master's theses, or whatever. And we can look at just the effect on impact. The money supply, right? We have the money supply is going to go to respond to the price effect, with this transactions, and the interest rate effect. And we can get the initial response of inflation. That's going to be the initial response of price, output, and the nominal interest rate. Put all those components in there, and we get that. On the one hand, there is a possibility that with a contractionary monetary policy shock, so I goes up. Usually, so if I goes up, then M is going to go down. Which is important. This gives us this liquidity effect. We have a contractionary monetary policy shock, so we have inflation and the output gap going down because of monetary policy, which is associated with a contraction in the money supply and an increase in the nominal interest rate. These relations are exactly the directions that we would have expected from ISLM. The reason why that's so important is the reason why they're put into ISLM is that the empirical evidence for the liquidity effect is pretty strong. And we found models in the interim and the time between ISLM and the New Keynesian model that were unable to consistently recover this liquidity effect. Right? So it's a great achievement that we can still, look, we get the same qualitative relation between these variables, the same qualitative response that we would have gotten in ISLM. Okay, then the money supply changes over time as the response to the price level. Right? The response to the price level to a shock over time is going to be the cumulative inflation rates. Remember how I added, subtracted, price levels in between yesterday to get this sum of inflation rates. Right? That's what we're going to have with the money supply as it goes forward. All right, so let's take a look at that then. We're going to look at the impulse responses of an increase in the monetary policy shock of 25 basis points for a set of parameters. Right, so we have this phi pi is greater than 1, it's equal to 1.5. We have a response to the annual output gap of 0.5, which if we look at the quarterly value, we divide through by 4. semi-elasticity of money demand. We have log preferences. We have alpha is equal to 1/3. And so the capital share of income is about 1/3, and labor share of income is 2/3. This is a number that's surprisingly, this would be very interesting for me to see what it's like in Vietnam, which is a different set of economy, a number of different pieces, or from a number of different perspectives. If you look at look at labor share of income in different countries. So we have the United States and Denmark. Okay, so they're both Western countries, European countries, but the United States has a very small public share of GDP. So the government is relatively small in the United States, despite all the complaining in America that it's too big. It's something like 12%. In Denmark, that number is about 50%. Denmark is one of the largest, at least in Western economies, one of the largest government shares in the economy. And we see that not only are their labor shares very, very similar, almost exactly the same, also very constant across time. So you look at this number and you look at what's happened in the United States since 1970 to 2004. There's huge changes in the U.S. economy and government, but labor's share of income. So what if we look at all of the money that goes to paying workers and see what share of our total national income that is, that number is about 2/3. Right? And it's amazing, right, how consistent that is across countries and across time. Right? I have it's a little longer series, that's fine. Yeah? I mean, this is just comparing, so Denmark would be considered, by European standards, of one of the more socialist countries. The United States is arguably the poster child for the least socialist and most capitalist sort of society. And despite that difference, the amount of our national income that goes to workers is very similar between the two countries, which I find just stunning. Right? And this is based not on, or this comes or results not perhaps because of different political processes, because this has been so constant despite political changes. It's probably due to some underlying mechanisms in the way production works. But in any case, I'd be very interested to learn whether that's similar or completely different in Vietnam than in these countries. But in any case, so we have the number here of 1/3 of capital share. so 2/3 of labor share of income. We really don't have a choice of another number if we're looking at a Western economy, because as we saw, all of them have this number, and it seems to be constant across time. So, yeah, that's the reason that. So now we can look at the impulse responses. Now we have the dynamics. We have our prices today, front-loaded future expectations of marginal cost, but it's spelled out explicitly mathematically, right? This weighted average, and the weights are determined, right, by our parameters. We have our beta here, our discount factor of 0.99, which means we discount by 1% on a quarterly basis, so roughly almost about a 4% annual real interest rate would be the natural rate of interest based on our impatience. Right? And so the responses that we get, the 25 basis point increase in mu, which translates on an annualized basis to a nominal interest rate that should have gone up by 1. This would be a 1 percentage point increase in the annual interest rate. So remember, if we have a quarterly interest rate, it's between 1 quarter, and if this response or if we're going to measure this on its effect on annualized interest, remember we were comparing interest rates of 2-year interest rates or 3-year interest rates. We always express this in terms of the annualized, the 1-year equivalent, which would be dividing through by 2 to turn a 2-year interest rate into a 1-year interest rate, in the log approach. And so for a quarterly to go to an annual would be multiplying by 4. Right? So this is here expressed in annual terms. This is the annual nominal interest rate that the direct effect of nu, 0.25, should have translated into a direct effect would have been an annualized interest rate that would have gone up by 100 basis points, but it didn't. It only went up by about 0.45. Why did it not go up by 1? Because we have this indirect, this general equilibrium effect. We have this contraction in monetary policy shock push down the output gap and push down inflation, right, which is what reduced the magnitude of the response of the nominal interest rate. Yeah? And we have the output gap. Right, so again, this way of thinking in terms of a 1% is right, you could do this some program with Dainaire will always normalize these to a 1 standard deviation shock. Right? For us, many times it's useful to think of a 1 percentage change. So a 1 percentage point increase in the nominal interest rate, and this causes inflation to go down by 1/3 of a percentage point. Right? So just you can see the magnitude of the effects. Right? So annualized inflation went down by 1/3 of a percentage point. The output gap also went down by about 1/3 of a percent. Now this, you can figure out, you can read you can see the internal consistencies here. So inflation in the first period after the shock is about 0.18, minus 0.18. So if we take the nominal interest rate here at about 0.4, and we subtract minus 0.18 from that, i.e. if we add 0.18, we're going to get a number that's about 0.6, which is the real interest rate response here. So it's, of course, by construction, since we're doing it mathematically, it's all going to be consistent, right? So we can look, expected inflation from the shock is 1 period ahead, we can go to another period. So expected inflation 2 periods ahead, and connect it to the nominal interest rate next year, or next period, and that's going to give us the expected real rate the period thereafter. Okay. All right, we see money growth on impact goes down, and then it's positive. So what this means is that the money growth level falls, and then slowly returns back up towards its initial positions. We have the growth rate is positive, or negative, and then positive. That's maybe useful to trace this out. So if we think of so this means that the level of m starts here. Right, so this would be our drop in the level, this negative growth rate, but then the level starts to converge back. And so here we have a negative growth rate, and then here, period on period, it's increasing back to where it started. Right, so this is back to our ISLM theoretical evidence of the liquidity effect. We have the reduction in the magnitude of the response of the nominal interest rate because of this systematic response of monetary policy. And with the fall in expected inflation, we can also see the fall in expected inflation. Since inflation goes down and is expected to remain go down, we have that the response of the real rate is larger than the response of the nominal rate. Okay, how about we take a 10-minute break, and then maybe we can use computers together. We're going down there and look at these figures together and see maybe what happens if we change some variables, some parameters, if monetary policy reacts more strongly to inflation, or is it a more hawkish monetary policy, right? Or maybe if we have some different elasticities in the underlying economy. So a 10-minute break, and then